Okay, let's start again. So the next thing I want to talk about is what is called score matching. I should turn on my mic as well. Can you hear me now? Sorry. Sorry. It's just above my cognitive load to stand here. Yes, sorry. Yes, okay, score matching. Yes, I mean, I have to make a confession, and there's much more to stochastic differential equations and stochastic processes than I have told you about. One very important property that is used in this score matching approach is that you can actually define equivalent stochastic differential equations that both run forward and backward in time. And here's a snapshot from a figure in a very famous paper on score matching. I'll link to it up here, where this property is used explicitly to define the objective that we learn. So this is a different notation than we use, so I will not spend so much time on kind of going through the actual kind of math in this figure, but the important point here is that you can define a generative model going from noise to dogs, and you can also define an equivalent process that runs the other way. And these two processes are kind of related in the way that it's kind of the same model components, and the only thing that kind of differentiates them is that you have to add another term in the stochastic differential equation that depends on what is called the score function. And the score function is that you take the log probability, your log marginal probability, and then you apply this gradient operator here. So the gradient is with respect to the stochastic variables, right? So if you have d-dimensional stochastic variable, then this score function will also be d-dimensional. And in score matching, what we do is that we actually kind of, in the way that I will explain it, is that we massage this diffusion objective in such a way that it's an objective to learn to approximate this score function. And it uses this very famous fact that you can actually define a stochastic process going one way or a stochastic process going the other way, and these will kind of sample the same paths. And of course, probably a lot of you have seen kind of ordinary differential equations. And ordinary differential equations, they don't distinguish between going one way or the other. It's kind of trivial. You just say, okay, I start an initial point, and then I can kind of solve my equation forward, or I can solve it backward. But when you have a stochastic process where you add noise, it's kind of non-trivial that you can actually define like a procedure that gives you the same result going forward or backward. Yes. Okay. And all this stuff follows from a very famous equation called the Fokker-Planck equation. I have kind of given a 1D derivation of that in the bonus material, but we will kind of just use kind of our result from the previous lectures to derive this. And it's very much kind of the important thing here. I mean, I also said that already. The score function is kind of the gradient of the log of the marginal distribution. So that is kind of the important quantity here. So remember the way that we kind of run the SDE, the stochastic differential equation, forward for the variational distribution. First, we initialize it at t equal to 0, and then we draw a starting point, and then we run this equation with small delta t's forward in time. And every time we kind of, in every step, small step, we add some noise that has a variance dt. Yes. So this is also if we kind of run this backwards, we can also, of course, we can also define a stochastic process that runs backwards, right? So we could actually have started the process by sampling from set 1 from our variational distribution, and then define a stochastic differential equation, now with a new drift term where I put this kind of arrow on top that indicates that it's kind of a drift term for going backwards in time. I should also say I made a small simplification that is used very often in this kind of game, is that just to have like one variable, one kind of variable, not a vector or matrix for the sigma, and then make that sigma independent of the stochastic variable. So it's just a standard deviation that depends on time. And if we then define this stochastic process that runs backward in time with delta t negative to have the same, we can choose that to have the same variance here. And then standard deviation, and then the kind of the reverse time Wiener process is like a Wiener process, so it is like independent Gaussian noise, and then with the same kind of variance that we had before. I just put an absolute value here because now delta t is negative. Yes. So we have these two processes, and this process here is called a diffusion process, because it's kind of a process where you kind of, when we start from data, we're kind of destroying the data. We're adding noise as we go along, and usually, as I also showed in the kind of example with kind of solving the SDE equations, right? Then we actually start, this distribution is started, set 1 here is very close to the corresponding data point x. So this is a diffusion process. So in this nice drawing, it corresponds to kind of running this way. So this way. Yeah, they call it forward, I call that backward, but that's just kind of a convention. But you start with the image, and then you have this kind of stochastic process that kind of destroys it over time. And that is this kind of in my notation, backward process. Yes. Yes, and actually, as I said already, for a particular choice of G and this kind of backward G, then these two distributions will become the same. And the equivalent version has this kind of so-called score function here. So we add something proportional to the kind of variance of the process, and then we take this gradient with respect to set t of the log of the probability, right? So kind of the nabla here is kind of the gradient vector, right? So the first component of this gradient vector is the partial derivative with respect to the first dimension, and so on. Yes. But this is a very fundamental result. So that means actually, if we know the score function, and if we kind of have defined this one, then we actually also know kind of the forward drift, right? So we could actually define the function, right? That is actually what we do in the next slide, right? If you look at this diffusion term, it depends only on f minus g. Now I've used kind of, this is kind of the norm of the vector squared here. So if I write my g in terms of the score function and the backward, and I then choose my generative model to also have the same backward term, but then with, of course, this is kind of this is the score function for the variational distribution, and f here should be defined in terms of the score function of the generative model. I don't know this one, right? This is very important, right? I know f, but I don't know p. There's a kind of non-trivial relation between the two. But I could then kind of say this I don't know, but then I could replace it by a neural network, and that's essentially what you do in score matching. So if we do that and call that S, right, then we can actually plug these two expressions into our diffusion laws, and then we end up with this laws here, right? And since we have chosen Q to be a simple distribution, we actually know this one, and S is not known. We can replace that with a neural network, and then we use this term here for the diffusion laws. And once we have kind of learned this in kind of very similar way as we learned the diffusion model, then we can find the generative model by using our definition here, and then solve this as in the same way as the pseudocode that I showed for the diffusion model. So this is essentially score matching. Define a function here, the score function, and then calculate kind of this kind of laws here as a difference to this kind of known score for the variational distribution. It can also be derived in a different way that I have not talked about, but that's for another day, for another course. So the last thing I want to say something about in detail is kind of shifting gears a little bit and talk about ordinary differential equations, and then talk about how we can actually use neural networks to make these kind of differential equations very flexible, but essentially solving the same problems as we have solved with stochastic differential equations. So let's go and define the ordinary differential equation. So it's essentially the same as the stochastic differential equation, just without the noise, right? So it is a deterministic equation. You get a C, you plug that into this drift, so-called drift function, you take a small delta t, and that gives you kind of the new set, right? You have here, I have used this kind of delta notation here, or d notation here. This, when you look at the equation like this is not really defined mathematically, but it's nice because it looks like the way we defined the stochastic differential equation. And the reason why it's not really mathematically defined is that when we go to this infinitesimal limit, right, we take delta t to 0, so that means that the right-hand side in a way is trivial, becomes 0, and then also the left-hand side then consequently becomes 0. But of course we know that this is just kind of a convenient notation for actually writing it like this as a differential equation, and then this equation actually makes sense, right? That the time derivative of the stochastic variable is determined by this drift function here. Yes. So as I kind of, let's try to pick it apart, right? Delta t is like this kind of going to 0 time step, and we can both let delta t be positive and negative, so we can actually solve, kind of trivially solve a deterministic equation forward and backward in time. We can run it on a computer, then we actually just take delta t to be 0.01. That's kind of in the kind of assignments. I think that's kind of what I use there. And dc is a change in c, right? So that is actually just a shorthand for writing c of t plus delta t minus ct. So this is another way to write, a more computer-friendly way to write the equation. Yes, so how can we use this as a generative model? We can use it as a generative model because the very first value of C0, we can still say that comes from a distribution, right? So that means that also means that kind of there will be a distribution, even though this is a deterministic relation. Of course, since this has set 0 is a stochastic variable, then also set t is a stochastic variable, right? And then in the end, we can kind of draw, once we have set 1, we can draw x as before. So it's kind of the same, exactly the same stuff as we do for the stochastic version. Also, we can view this as kind of like what we call a residual neural network, right? Because we said that the new set CT is equal to the old CT plus some kind of residual, and this residual is simply given here by the drift functions times delta t. And as we talked about before, right, we have this parameter sharing, so we use the same neural network for all kind of time points by using t as an extra input to our neural network. Yes. I should also say that the simple way of actually kind of integrating the equation in this way or this way actually often doesn't work. It kind of numerically, if you run, for example, you can try it, but if you run, for example, this ODE notebook that I've given you with this simple so-called Euler integration, and you train the model, you'll see often that actually numerically it breaks down. So you have to use more advanced methods under the name of Runge-Kutta. And these methods are like kind of what we call higher order methods. So that means that every time you do some kind of discretization, so you use a finite dt instead of kind of very small dt, going to 0 dt, you make an error. And in the Runge-Kutta methods, what you do there is that you make sure that kind of these errors are kind of smaller. And kind of mathematically, you can prove that they are smaller. So you can write kind of the error in terms of dt, and then you can show that kind of Euler integration has an error which is order dt, so it scales with dt, whereas kind of a Runge-Kutta method, kind of the simplest Runge-Kutta method, scales with dt squared, right? And if dt is 1 over 100, right, then dt squared is 10 to the minus 4, so it's much, much smaller. But you have to pay a price because you have to evaluate the f function more kind of more times than you did with the Euler method. Yes. Then there's of course the question about how can we learn this model. Right now I just defined the nice generative model. How can we learn it? And then we will still want to learn it by maximum likelihood, and then we have to kind of integrate out all the values of C. I will actually kind of omit this and just, in interest of time, it's still also based on like a lower bound on the log likelihood. I'll omit all this nice stuff. It's very nice, beautiful stuff. And then in the end, just go to the algorithm, right? So now, as I just said that you should not trust this simple way of integrating, but let's just use the simple way of integrating. So you can see that's what is done here. That is the simple Euler-based solver. Actually, in the case of the ODE, we cannot no longer do this simulation-free stuff. So we actually also have to, while we are integrating the equation, we should also do a little bit of bookkeeping in order to, maybe I should just give the final equation. So actually, these are kind of the equations you have to solve to get both the elbow and the set, and you can do that by kind of joint integration. So you can see this is kind of integrating the differential equation, and this is like integrating to get the log likelihood. But you have to kind of integrate all the way in order to do that. So it's no longer what we called before simulation free, that you just can choose a random t and use that as a proxy for the whole integral over t. Here you actually really have to carry out the integral over t, and that also means that running the ODE, that's kind of the biggest disadvantage of this method, is that you actually have to kind of solve the ODE, right? So that's also why at the SDE-based versions of these methods are much more popular, because you can do this kind of simulation-free learning. Yes. You can also calculate the elbow, and to calculate the elbow, you have to also kind of solve the ODE in order to get this elbow term coming from the integral, right? So this is kind of what you do here is kind of the equivalent of what we did with the diffusion term in the stochastic version. But the rest of it looks a lot like what we had before for the STE elbow. Then to sample, it's like I said already, we sample a new data point, right? We sample first at 0, and then we solve the ODE. Yeah, that was another detail I didn't mention here, but you actually have to solve, in order to get the log likelihood, you have to start from the data and then solve backwards in time. You can see here you have a delta t, which is -1 divided by t. But in order to, of course, get data, you start from set 0, and then you have to solve forward in time. And then in the end, again, sample from the likelihood function. Yes. So here's an example, again, the same example as before. And now you can see that everything is straight line, is not straight lines, but there's no, this kind of noise you had before from the stochastic is gone, because everything is deterministic. So here you can see how these paths look once you have kind of learned the model, and you can see it's kind of okay approximating also the distribution, maybe not quite as good as the stochastic version. So let me see now without glasses. Yeah, so the backward is kind of solving the ODE from the data backward towards the prior, and the forward is kind of going forward. And in this case, these two are exactly the same, right? It's deterministic, so you can actually say, okay, this point here at t equal to 1 corresponds to a point here at t equal to 0, and if I then kind of reverse time and solve back again, I will kind of get a path that coincides exactly with the original path. And that was in the stochastic. I talked about this score matching. In the stochastic version, this is only kind of true on a distribution level, right? That the distributions you get in the end will be the same. Yes?
Would this be a good result in general? Like I can see that the prior samples and training data is matching perfectly, but the other ones, would that be a good, would that be successful, or how would we determine? Because yes, there are some, it's aligned to some data,
Yeah.
but it's also very different from each other.
Yes. Yeah, I think this is not the best result I've seen, but that was just what I...
No, just in general for understanding. Like
Yeah. I think it's. I mean, I think, of course, I think. Okay, my very general answer is, when you do machine learning, you always compare. You should compare with different models, right? So you should find some other model and do this. I think this is in general a pretty. Okay, even though we have like 1,000 data points or something like that, so we have really sampled this distribution a lot, right? But in general, this is kind of a little bit a difficult question, because this is kind of, even though it's a one-dimensional distribution, it's a multimodal distribution, right? And it's also like, it's not Gaussian, it's kind of Laplace, so it has a different kind of tails, right? But I would say no, this is not a super good result. I mean, so that's the short answer. Not super good result. You would like to see something better. I think also in the program we calculate like what, because we know the ground truth, so we can calculate what is the kind of ideal log likelihood, right? And we can compare that to the number, the elbow we calculate. So we can also compare these two numbers directly, right? And that's also a very good proxy for whether it's actually a good approximation. Yes. Okay. So the last thing I want to, what time is it now? Yeah. Okay. I'm doing good with time. The last thing I want to talk about is an alternative where we still want to use kind of this deterministic equations, but we want to find a more clever way to learn the model that doesn't require that we actually integrate the equations. And that is called flow matching. And here I want to make my second confession that there's even more I haven't told you about with stochastic differential equations. And this is also something that is kind of revealed in a plot from a figure made for the same authors that made this kind of score matching. So you can, if you look at this plot, you can see that there are some white lines in the plot, right? And it says that kind of the legend says probability flow ODE. So actually, my second confession is this, that there exists, for any stochastic differential equation, there exists a deterministic equation, differential equation, an ODE, that has the same marginals as the stochastic version, right? Right, so you can actually, so the marginals, remember again, the marginals is this kind of where we kind of, we see marginals here. We see one at t equal to 0 and one at t equal to 1, right? But I also had this other drawing. Where was it? Right, the marginals, come on. Yes, this. So the marginals is this kind of where we have, I mean, that kind of, now we have infinite kind of different stochastic variables, but a marginal is like when we slice at a certain time and look at the distribution there, right? So what this result says from stochastic processes is that there is like, even when we run a stochastic differential equations, we have these kind of very kind of noisy paths, right? But we can actually mathematically show that there's like smooth paths that will give the same marginals, right? So that's like the property that people use in the so-called flow matching to define like a learning objective that learns ordinary differential equation. So in this plot here, what the authors have shown is that you can see you have this kind of you have an STE that defines these kind of very noisy kind of paths, and then you have an ODE that defines these very smooth paths. But these two will actually, if you kind of slice the distribution and find the marginal, they will have the same distribution. And that's a pretty kind of, maybe you would not have guessed that if you just kind of said, oh, very noisy path, how can I actually find something that would be deterministic equivalent to that? But that exists. And it's actually a very kind of simple result in a way. So here I've written down, again, it's a consequence of this Fokker-Planck equation. So I have written down here 3 different equations. So I started out with like, now I use kind of this arrow here to indicate that this is like the drift for a forward time stochastic differential equation. Then I can define an ODE. You can see now I've kind of dropped the stochastic term. So this is a deterministic equation corresponding to the kind of white lines here. And it has a different drift. A drift now where I subtract like sigma squared half and then times the score function. And here I can also define the equivalent. This is, okay, so I mean that's an important property here. So I can also define the equivalent kind of reverse time stochastic differential equation, right? And the forward time and the backward time differential equations, they have the same path distribution, right? So path that kind of, these kind of rugged paths will look the same for these 2 differential equations. Definitely like the ODE will have very, very different paths. There will be this kind of smooth path and defined by this kind of deterministic stochastic, deterministic differential equation, right? But all 3 equations have the same marginals. And that's kind of the amazing result. And of course, it still requires here that we know this score function, or maybe not. Maybe we can actually define it in a different way. Yes. So what we do now is we kind of go through the same exercise as we did with score matching, that we take the diffusion laws we know from our diffusion models, and then we rewrite that in terms of a flow, and the flow is nothing but the drift function in the ordinary differential equation. And this is done here. And I will not go into the details, but in the end, you get this very nice, simple result that actually the flow that you want to learn, this is kind of the unknown defined by neural network, has to be matched with kind of the flow you get from your variational process. And often in flow matching, the way that you write down, you don't write down this variational distribution explicitly because the derivation is kind of coming from a different place, but it's actually chosen to be this very simple form. So you can see it's kind of, if we set t equal to 1, so that is like when we are at kind of close to the data, then it's actually kind of spiked to the data. So I mean set 1 will be equal to the data. And then when we move away from the data, then we kind of weigh down the data, and then we kind of add more and more noise. And if we kind of make this choice, we can actually write down this drift function here in this simple form. And you can see it's a little bit problematic because, I don't know, it's not problematic, but I mean, in a computer program, it's problematic to set t equal to 1. Kind of mathematically, it's not problematic because then, you can see here z is actually kind of equal to x, so it'll be 0 divided by 0. So normally when you implement this, you add a small epsilon, so you avoid these kind of close to 0 divided by 0 encounters. Yes. Yes. But then apart from that, you can see now we have this, since we have this kind of diffusion laws where we can use this kind of simulation-free approach, then it means that we can actually now learn the flow, and then we can learn that simulation-free. And once we have it simulation-free, then we can use our favorite numerical integration method to kind of just get these kind of white paths instead of having to use kind of the noise. And if everything works out perfectly, we can actually do something even more brilliantly. We can draw data from the model either by using the ODE, the white paths, or using an SDE, kind of the rugged paths, right? So that's kind of nice that there are two equivalent ways of getting data from the model. Yes, okay, I made it to the end. Are there any questions to the stuff I sprinted through here for now? Otherwise, I will kind of move to. Yes?
In the ODE algorithms, there was like a placeholder. I didn't quite catch what that was.
Yes. Okay, that's because I try to be clever. That's because I reuse the same solver to both get my log likelihood lower bound, and I also use, and there in that case I need to run it backward from the data towards the prior. Once I want to sample data, I don't want to compute the elbow, so I kind of don't return that value. So it's just me trying to be clever. Yes. But good point. Yes. Okay, but let's go to the wrapping up. Yes. So if you remember back when the course started, I tried to kind of make my sales pitch say that, if you spend time on this very difficult topic, then it's actually something that can really benefit you both while you're at university and also later on in your life if you ever leave university. And my sense is that you have kind of followed my pitch and been dedicated, so I appreciate that a lot. One thing I would like to actually discuss with you is this thing about, is kind of generative AI actually useful for us becoming better at what we are supposed to be good at here at the university? I don't know, the verdict is really out there, right? I only experience in my own kind of work, both doing research, but also like preparing teaching material and so on, that it's super useful for me to have good generative AI models like Gemini or ChatGPT to help me. I also experience sometimes when I have conversations, especially I think ChatGPT is too chatty in a way. It writes too much, and I have this tendency to just copy and paste whatever I can use and not read all of it, right? So maybe there's also this danger of not kind of deep learning, let's call it that, when we use these tools. So I don't know if any one of you have kind of, what is your feeling? Is it too tempting to make you kind of just answer your homework fast, or is it actually something that helps you learning? I would like to hear if any of you have given this some thoughts. I mean, if you admit you have kind of been close to the deadline and you've cheated a little bit, it'll stay in this room. Yes.
Well, I do use it mostly like I would use a TA, or I would use the internet. Like if there's something I need to explain again from a lecture, or a concept I need to explain in a different way, I ask it.
Yeah.
Also, if there is something that I need help with, like preparing for the exams, like if it's verbal oral exams, like okay, what are the subjects, what can I get into? It helps me organize it. I use it as a tool. I don't use it as my final product in any way.
No.
Because it can be wrong in so many ways, and it often is. So it's important to read through it and understand, okay, this is incorrect. And you try to, it's important to also tell it if it's incorrect or you believe it, because it can easily be incorrect because it misses something or doesn't know all what you know.
Exactly. And maybe you have not provided enough context or something like that. I agree completely, and I think this is really the right way to do things. I think I've had a few times the TAs came to me and said, "Hey, I have a suspicion that they have actually used the generative model to generative AI to make the final answer." Right? For example, one TA said, ChatGPT likes to put boxes around equations, and now there's boxes everywhere in this answer. And I think that's just the wrong way to use it. So I agree very much with what you say, right? That we should really we should vouch for the final product and then use it to get to the final product we write ourselves. There's also, I think there's a lot of kind of this thing about you have kind of memory in your hands. If you write down things yourself, then it actually really is you who are doing it, right? And you learn from that. Yes?
Yeah, second it. I mean, if you take a slide or a given lecture, reading that, trying to understand that, digest that, it's honestly there'll be a lot of blanks. And these models, they're designed for filling in the blanks.
Yeah.
If you give it give it half a slide of text and say, okay, explain this step by step, and I actually think it gives you very good bearings, because you start understanding what are the pieces, and you might lose that, you might miss that because it's not all written in the slides. But when it may be redundant, so you skip the 4 points that you actually did understand, but the fifth, which was important but you missed, you tie that back.
Yeah. I would like to come a little bit with a counterpoint, which is actually was something I noticed in the assignment. I agree with what you say in general, but I will just try to provoke you a little bit. So in the assignment 4.1, there was this thing that we should go through a different number of amount of hidden layers, right? And actually, when you go to 5, at least a lot of people encountered like numerical problems, right? I mean, I don't know if you also encountered that it kind of didn't converge, right? And I think there you could probably also ask the large language model to kind of help you, but maybe sometimes, or maybe your TA was one of the TAs who found a solution with gradient clipping, if you haven't solved it yet. But there's also some value in actually sitting down and being really frustrated and then figuring out yourself, right? And this kind of friction, you remove that a little bit.
Well, there are different use cases.
Yes,
I mean, one is
but but we are all human.
With heavy math, another is trying to code, and on the second point, I agree.
Yeah. I mean, but we are all tempted. If we can remove friction, we'll do it, right? And maybe then we'll not. Maybe I don't know. Because I grew up. There was not even internet. No, I should not but I mean, maybe we can remove too much friction. I don't know, but it's a super. I agree with what's been said, and I think it's an important discussion and something you should always. These tools are not getting worse, right? So you should always kind of feel back and say, okay, why did I actually go into university? Go back to the basic question. And then if you're starting feeling, okay, I'm actually just surfing through my studies because I'm super good at prompting, then maybe you should reconsider your strategies, right? Because the important thing is, in the end, both for me and the university and for you, is that at the end, when you leave the door, right, you have you're superhuman. You have some powerful skills that can change the world and so on, right? And maybe there are different ways to get those skills, and we are not always choosing the right way to get there. Okay, so I just want to kind of reiterate what is it that we have actually seen in this course, right? So we have seen a lot of things coming from many different places. So we've seen probability, we've seen a lot of linear algebra, we've seen optimization, we've seen learning algorithms, we've seen architectures. Remember this thing about, like, when you choose an architecture, think about what is the inductive bias. We also in practice kind of done a lot of Python and PyTorch programming, a little bit of MLOps, HPC challenges. This is kind of at least what challenges me as a very, very busy professor, is that I don't really have the time to become good at kind of running my experiments on HPC, and I think that's definitely also kind of what is probably missing sometimes when I meet you guys later in special courses and so on, and then I say, oh yeah, you should just do this and this and this, and all this and this and this usually requires HPC, and that's something that we really haven't kind of. We have kind of tasted a little bit, for example, in this kind of LLM exercise. Right now we start getting a little bit bigger models. We have to find somewhere where we can actually run them. And you definitely have to learn that also elsewhere. We talked about that already, that we use large language models. Yes. So what, if I kind of, I always try to a little bit keep my kind of material up to date, because I think that's kind of exciting. I mean, I don't want to talk about CNNs when everyone uses transformers and so on, right? But I think one of the things we have not covered really here is kind of reinforcement learning, and also like reinforcement learning like ideas for fine-tuning large language models, right? I think this is really where all kind of the progress we see nowadays in ChatGPT and so on, they're actually working a lot on finding clever ways to make models reason and so on. And that's maybe something in the coming years we will cover a little bit more. Yes, and the last thing I want to say is that there is some kind of evaluation of the course, and we are heavily encouraged to tell you guys to remember to fill it in. And that's all I wanted to say. There's some bonus material for those who are really eager, but also a warning, a sign that, yes. So remember to fill in the evaluation. Thank you.